Hello, and welcome to Science with Mr. Morgan. In today's episode, we're going to talk about the solar system, part 1. Let's start by talking about tides. Tides are daily changes in the level of ocean water here on Earth. Now, if you've ever been to the beach, you may have noticed that at different times of the day, the water level at the beach seems higher or lower than usual. And that's because the ocean is constantly moving between the high and low tide phases. A high tide occurs when the water reaches the highest level of the day, while a low tide occurs when it reaches the lowest level. And this cycle of going from high to low and back again typically happens 2 times a day. But why do they occur? Well, the main cause of tides is the pull of the moon's gravity on Earth. The water on the side of Earth facing the moon is pulled the hardest, creating a bulge, and this is a high tide. The Earth itself is also getting pulled slightly towards the moon, which causes another bulge on the opposite side, aka another high tide. Now, these bulges on either side of the planet pull water away from the other areas, and in those other areas, it creates low tides. So when you're at the beach and the water seems to be moving away or coming closer, you can thank the moon's gravitational pull for that. But what about the sun? The sun is way bigger than the moon, so wouldn't it have more of an effect on the tides? Surprisingly, no. The moon has a much greater effect on Earth's tides because it is so much closer to us. It is closer in proximity. And when we talked about the fundamental forces of the universe, and the force of gravity specifically, we touched on how proximity of an object can have more of an impact on gravity than size alone. That being said, the positions of the sun and the moon together can influence the tides, which results in spring tides or neap tides. During a new moon or a full moon, the sun and moon may align in a straight line, and when this occurs, it produces something known as spring tides. These result in very high tides and very low tides, creating the greatest tidal range between the two. During the first and third quarter moons, the sun and moon are at right angles to one another, which pulls the oceans in different directions. And this ends up leading to neap tides, where the difference between high and low tides is much smaller, creating the weakest tidal range. But let's move on to the largest object in our solar system, the sun. Our sun is a star. It is a giant sphere of plasma held together by gravity. It provides heat and light, and those two things combined with other factors are what make life on Earth possible. But without the sun, we wouldn't have life as we know it. It is also the center of our solar system, making up 99.8% of the mass in it. Now, this means that all of the planets, moons, asteroids, everything else in our solar system combined only make up 0.2% of the total mass. So what is this massive object actually made up of? The sun is mostly made of hydrogen and helium, and it doesn't have any solid material. Most of its atoms exist as plasma, which is a superheated gas with an electrical charge. Now, even though it doesn't have a solid surface, the sun does have different layers. And let's break these layers down. So we're going to start with the inner layers of the sun. And first up, we have the core, which is the very center of the sun, and this is where nuclear fusion happens. Specifically, this is where hydrogen atoms fuse into helium, releasing massive amounts of energy which radiate outward. And it's incredibly hot, around 15 million degrees Celsius. Now, this process powers almost everything in our solar system. Next up is the radiative zone, which is the middle layer, so core, radiative zone. Energy moves very slowly through this layer. So slowly, in fact, that it can take a photon, aka a light particle, up to 50 million years to pass through this zone. And the temperature here is significantly cooler than the core. It's only 4 million degrees Celsius. Now, after the radiative zone, we have the convection zone, which is the outermost part of the sun's interior. Hot material from the core rises to the surface, cools down, and then sinks back to be reheated, which creates a convection current. And this movement of hot and cool material helps transfer energy to the sun's surface. And speaking of the sun's surface, let's talk about the outer layers of the sun. So first up, we have the photosphere, which is the visible surface of the sun, aka the part that we see. Surprisingly, it's actually one of the coolest layers. It's only 6,000 degrees Celsius, which is a lot for here, but a lot less compared to the core. Now, above the photosphere is the chromosphere, and it's about 2,000 kilometers thick and glows a reddish color. Now, even though it is heated by the photosphere, the temperature ranges from 4,000 degrees Celsius upwards of 10,000 degrees Celsius, so it could be a little cooler than the previous layer or significantly warmer. It can also shoot jets of gas at speeds of up to 72,000 kilometers per hour. Now, the final layer that we're going to look at with the sun is the corona, which is the outermost part of the sun's atmosphere. And this is the sun's halo, or crown, which can be seen during a solar eclipse. It's actually much hotter than the photosphere, reaching temperatures of 1 to 3 million Kelvin, which I know is different than Celsius, but it's another measure of temperature that scientists use. And this corona extends millions of kilometers outwards into space. Now that we've covered all of the layers of the sun, both inner and outer, let's look at surface features of the sun's surface. There are sunspots, which are cooler, darker areas on the sun's surface that appear in an 11-year cycle. These form when loops of the sun's magnetic field break through the surface of the sun, and they usually occur in pairs. Solar flares, however, are violent explosions that release huge amounts of energy. These can knock out power grids, disrupt satellites, and affect cell phone signals. And they can also be dangerous to spacecraft and astronauts because they don't have the magnetosphere protecting them like we do on Earth. And these are caused by the sun's magnetic field breaking. There are also solar prominences, which are loops of plasma that extend from the sun's surface outward. They can reach thousands of kilometers into the sun's atmosphere and can last from a few days upwards of several months. They can also be seen during total solar eclipses. Now, there was something known as the Solar Dynamic Observatory, which was launched on February 11, 2010, to study the sun's magnetic field. Specifically, we wanted to look at how the sun affects Earth's atmosphere and climate. And it provides extremely high-resolution images and gathers data very fast for scientists. Now let's step away from the sun and the Earth and shift our focus to the solar system itself, specifically our solar system. Our solar system consists of 8 planets, 5 dwarf planets, and over 150 moons and countless asteroids and other smaller objects. So here's a quick rundown of our planets. Mercury is the closest planet to the sun, followed by Venus. It's the second planet of the sun and covered in thick clouds. Then there's Earth, our home planet, full of lots of life, third rock from the sun. Mars is the cold red planet with the tallest volcano in the solar system. Jupiter is the biggest planet with a massive storm called the Great Red Spot. Saturn is the famous ringed planet. Uranus is the sideways tilted planet. And Neptune is the farthest planet from the sun, known for its deep blue color. Now you might be saying, Mr. Morgan, what about Pluto? Hold on a second. Beyond the planets, we have what are called dwarf planets, like Pluto, Ceres, Makemake, Haumea, and Eris. And let's not also forget about the asteroids and comets that travel through space. In later episodes, we'll get into the nitty-gritty of what makes a planet. But for right now, all we need to look at as the planets as a whole is that they all orbit the sun in elliptical or oval-shaped paths. It's important to note that the farther a planet is from the sun, the longer it takes to complete one orbit. And this is why Mercury orbits very quickly, whereas Neptune takes 165 Earth years to go around the sun one time. And that brings us to the end of today's lesson. Until next time.